Well, welcome everybody. So my name is Arjan Buick, and I will first give you a small introduction into Simufact company, the software products we have, and a few examples. After which we then give the control to Jens, who will give you a live demonstration of the Simufact welding software. So we are a company that's located in Hamburg, Germany. We're an independent international software vendor and founded in 1995. Apart from our offices in Germany, we have an operation in the Americas, for which I'm responsible. We are located in Detroit area, and we have also local sales and customer support in San Diego, Montreal, Mexico City, and for South America, Sao Paulo, Porto Alegre in Brazil, and Buenos Aires in Argentina. Furthermore, we have offices in India and China and operate a global reseller network. The software products we actually have two software products. One is called Simufact.forming, which is used for all kinds of metal forming. Can be bulk forming like hot forging, cold forming, or it can also be sheet forming, tube bending, all kinds of metal forming processes. And then secondly, we have a software called Simufact.welding, which is the focus of today's webinar. And I want to mention that both these softwares are built on top of the Marc solver from MSC Software. And that's where we have a lot of our collaboration going on at the software development side. So in addition to these two software products, I want to mention a very important module, which is called Simufact Premap, which stands for Prediction of Material Properties. And that module can be used in both the forming software and the welding software to look at aspects of phase transformation, grain size prediction, and things like hardness prediction. And I'll show you an example of the martensitic hardening that can be predicted by this module. A few words on the history of the Simufact welding software. It started in the early 2000s when the research group welding simulations of these automotive OEMs in Germany realized that they did have access to good solver technology for welding simulation, but they did not have a good graphical user interface to impact the production design and the design of the welding manufacturing process. So they knew our Simufact forming environment, and they realized that was a very good environment, and they ordered with us the creation of a similar environment for welding simulation. So we were ordered the creation of this software with its aim to be used close to production and to help them reduce prototypes. So several years of development went into the initial release, and in 2010 the Simufact Welding 2.5 came out, which was only for internal use by these automotive OEMs. After several iterations, a new release came out in 2011, which was provided also to some other partners of ours. And then in 2012, the first fully commercial public release came out, Simufact Welding 3.1. Going into a few examples to give you an idea of what type of simulations you can do with the software and what type of results you can get out of the simulations. I want to start with a very nice example of welding of a bogie girder. This is a part of the rail car, the rail industry. This example was created by one of our partners, Dr. Tobias Lohse, together with Dr. Ben Böse from Ulster in Germany. This model, here's the picture of the part, has 24 parts that are being welded together. So it includes 69 tack welds and 118 line welds. The total welding time is over 9,000 seconds. And if you add up all the total process time, you look at a process of over 30,000 seconds. So this is a very challenging process, but you can simulate that just fine with the software. And then at the end, you can look at these type of results. You can look at the peak temperature that every part of the model feels or felt during the welding process and then the cooling process. You can look at residual stresses, and you can look at distortions. And these are kind of the three typical results that people initially look for: temperature, stresses, and distortions from the welding simulation and the cooling after the welding. Second example I want to show you is very nice case study to study the effect of martensitic hardening on the structural strength of a weld. And this is where this pre-map module comes into play. So in this example, we have two thick plates that we weld together in a T-shape. It's actually laser welded from the top. So the weld zone is shown on the right side. It's very narrow. You see how the melt zone penetrates through the top plate into the vertical plate underneath, and you can nicely see how the mesh automatically adapts itself to correctly simulate the temperature effects. Now, if you look at the phases, then you see that during the welding, you initially get the austenite, and then as it starts to cool down, you get the creation of the martensite phase. And it's important to take that into account because martensite is stronger but less ductile than the ferrite phase. And on the right side, you see the two flow curves for each of these phases. Now, if you look at this case study where we did the simulation 2 times. On the left-hand side, you see the simulation where the martensitic hardening is taken into account, and on the right-hand side, it's not taken into account. So if after the welding, we remove the clamp on the right side and leave the clamp on the left side in place, that corresponds to loading up the structure. And you see that if you take the martensitic hardening into account, you get a much stronger structure. So if you zoom in on the weld zone, you can see the narrow area where the material was molten and it's actually joined. Then if you look at the most right upper hand picture, you can see that on the right hand side, that area, the metal did not melt, so it was not joined. So if you load it up, it just comes free, you open up a gap. While on the left hand side, even though it did not melt, but if you load it up, the simulation automatically detects that there's a contact condition and it will start to build up compressive stresses. So it's a very realistic representation of the welding phenomena and then the structural response to a loading. And the difference between taking the martensitic hardening into account or not is 20 millimeters. So it's a big, big difference. The next example expands a little bit on this combination of welding and forming. So you can actually chain the simulation done in the welding software with simulations in the forming software. And here we have another laser welding example. We can take the result and then put it in the forming software and do post-welding operations. Here a simple 3-point bending. But if you have a process where you have to straighten your part afterwards or you have to further bend it, then by these chaining operations, you can study the accumulation of stresses and strains from the whole manufacturing process. Reversely, you can also go from Simufact.forming to Simufact.welding, and this is also a very typical scenario where you first form a part by stamping simulation, for example. So here you see some cups, and then you weld them together. So here too, we did a virtual experiment. We said, okay, what happens if we take 2 shapes and we weld them together? You see one line weld there. This is without taking the forming results into account. And then we repeat that same process with the residual stresses and strains from the forming result. So immediately you see a very big difference in residual stresses, big difference in plastic strain. And what's very interesting, if you do a weld like this, the cap, the upper cap, will lift up on the other side of the where you have the weld, and the difference in the amount of lift is quite significant. So if you do not take the forming result into account, it lifts up by about 0.1 millimeter. If you do take it into account, it's almost 3 times larger. It's 0.3 millimeter. I have a couple examples that demonstrate how we are validating and have validated the software. There's a nice project going on at Mississippi State University in the U.S. together with an automotive supplier in the U.S. and it was sponsored by the Department of Energy under a project for lightweighting of automotive structures. If you move from the regular steel structures to more high-strength steel, aluminums, the distortion effects become much more prominent, and that's why it's important to study welding for these type of lightweighting efforts. So this was a very controlled experiment. Several cases were done, and several welds were repeated and measured. And on the right-hand side, you see the simulated distortion versus the experimental result. And you see that all the trends and the levels all look good. A very detailed paper will be presented later this year by people working on this correlation study. Second example is from an international round-robin test in Germany. This was a plate where a groove was grinded, and then 2 layers of a TIG weld were deposited in the groove, and then distortions and residual stresses were measured. And if you see in the picture on the right-hand side, if you look at my mouse, you see here through this cross-section, the simulation and the experimental data were compared. So distortions were very close. More importantly, here you see the curve of the residual stresses, and this humpback shape is captured very well by the simulation, and that can only be captured correctly if you correctly take into account the material behaviors. So in summary, before we go on with the live demonstration, what I wanted to explain to you is that Simufact welding is used close to design and production. You can simulate large and complex welding processes, and it's used for looking at prediction of temperature, distortion, residual stresses, looking at the effect of material properties, things like martensitic hardening, and then you can look at the structural response to loading after welding. So in addition, you can do a full chaining of the forming software and the welding software, and the results have been validated against experimental data, and I showed you a couple of examples for that. And all of this is available in a very easy-to-use graphical user interface, and that's what Jens will demonstrate to you right now.
Thank you very much, Arjan. At this point, let me transfer the control to Jens so that he can share his screen.
Okay, thanks a lot, Arjan. Greetings to everybody from Hamburg. I would like to go on now with to demonstrate Simufact welding. But please first let me allow you to talk a bit more about the calculations principles. When talking about welding processes, everybody of us might think about different types of welding processes and different aspects. For example, the difficult keyhole dynamics in a laser welding simulation, or about the material behavior during welding. So we divide welding simulation into 3 parts. And on the one hand, we have the process, and there are a lot of processes. over 100 different welding processes are recognized. So here there are a lot of different solutions for that. With Simufact welding, we focus on the structural behavior during welding. So, as Arjan presented, our aim are the temperature distribution inside of the component, and especially the distortion behavior. Nevertheless, we can't ignore that the material is changing and that the material is temperature or phase dependent, and therefore we are using our Simufact Premap modules to include that into our structural simulation. I will show you later how we do that and what a user has to do. And of course, we also have to model the temperature from the processes. Therefore, we are using mathematical descriptions to describe the introduced heat and the melt pool inside our structure. The principle is easy. If we have a transient moving heat source, we introduce the energy in small time steps, and after a small time step, we allow the heat source to move a bit onwards. This depends on of course, on the welding velocity and the weld pool length, and this is how we can model a transient moving heat source. And we do this step by step. We do a thermal analysis, then we know the temperature distribution and the phase fractions afterwards. We know the thermal strains. If the material has reached melting temperature, we have a glue by peak temperature. So the nodes will be connected, or node to surface will be connected. If we are over the solidus temperature, we will reset the plastic history. The molten material do not know a hardening history anymore. And then we do, using this, we are performing our mechanical analysis. With the information of the deformed mesh and the former thermal distribution, we can do the second analysis and so on. So this is really coupled. This is important, or this is necessary, because we have to take into account a lot of dependencies. One key to a good welding simulation are the material properties, and we have to consider the temperature, and also if we have steels, especially for the common struction steel, it's important. We have to consider the phase dependency. We can also include effects resulting from phase transformation, the transformation strains. We can also have transformation plasticity, and this also affects the material of the plastic history. If we have additional data, for example, there's often data available depending on the T8-5 times. In the times, the material needs to cool down from 800 to 500 degrees to predict hardness or proof stresses or even tensile stresses. Okay, please allow me to show you Simufact welding live. As Arjan explained, our main achievement is our graphical user interface. So if you open, I've installed Simufact welding, and if you open now Simufact welding, our GUI will be opened. And as I mentioned before, there are a lot of dependencies. Talking about welding, one might think everything is so complex. So we want to offer you a solution to make everything handleable and user-friendly. So the first thing I do if I install our software is I do some presettings, which will be used always. For example, the language is definitely important. Now I use English. In this version we have also German. There will be also Chinese version available in the next weeks, and we can do some pre-definitions of for the views and our working paths, and we can also, and that's for me the most important thing if I use such a software, I can define my own unit system I want to use. Of course, the solver itself has to use a consistent unit system. But if I work in a GUI, if I want to present results to a customer, I don't want to show my distortions in meters or my temperatures in Kelvin. So the program can recalculate everything, and therefore I do some predefinitions. For example, I want to use the length in millimeter, pressure and stresses in megapascal. So all the others are fine for me. I can change it, of course. We allow more than only these values, and we can also change the values during modeling when we activate this here. If we activate this check option. Okay, so if we want to start now to create a new welding project, or welding project, I click on project, and I can say, create a new one, or open an existing one, or one of the last ones. Now I go on new, and I can define my working folder, and I can define a project name. Let's call it MSC. Oh, I tried out 1, so now I get MSC 2. Okay. In the next step, another window will be opened where I can do some presettings. You will see this will make things very easy. You don't have to define your connect which surfaces where you have heat losses on the surfaces or where the surfaces are in contact. This will be done automatically by the program. But you have to tell him if you work in an oven or if you work in somewhere where it's colder or what's your room temperature. You have to define the direction of gravity, and you have to define, of course, how many components do we have. At least for welding, we should have more than one. Maybe we have a working table, fixing, clamping, and one robot. Of course, you can use much more, as you could see it on the, for example, on the Alstom project Arjan presented to you. Then you can make a small description, maybe text. Then you can say OK or apply. And then 2 additional new windows will be opened. One catalog window where all our items are described we want to use, and an Explorer window where a process can be defined. Now you see the name process. It's red because it's not completely defined, so I can fill it with the items from the catalog window. At first, I need, of course, some geometries. We can import geometries in the Nastran format as PDF files. I have prepared too small to show how fast I can build up a model. Of course, I have to tell him which unit I use, because it has to recalculate everything, and I can say if I have more than one, please use it for all geometries. And now the main principle of this program is that you can do a lot by drag and drop. This meshes for the first component, this for the second one. And now you see here a mesh. It's, the meshes don't have to be consistent. It doesn't matter. We use a glue by peak temperature contact. You see here we have already a predefinition of the ambient temperature. Here you can see on the free surfaces we will consider the heat losses via convection and radiation. And if they are in contact, we can also model the heat losses via heat transfer. Okay. We also have the possibility to move our components or to have a set. Yes. Move it now in one direction, maybe. I think it's only a small model. Okay. I can move it. Yes. Now my geometries are defined, and I have to tell the model or which material the components are made of. So therefore, we can go in the catalog tree on materials, right mouse button, and say we have the possibility to create a new material. Then we have to define everything by our own. Or we can go on our library. We have this library for all processes. For example, for welding, and if we select nothing, we have some predefined material files. We can use them, of course, and it's automatically imported to our project. We can also import material files. Here, for example, from JMAT Pro, we have a direct interface to JMAT Pro. And here there's a common structural steel. And if I open such a file, now it takes a bit, then you see, depending on the chemical composition, we can use can use a lot of material properties. For example, the Young's modulus, depending on the phases, we use a multi-phase model. We have, of course, our thermal properties, the specific heat capacity, the thermal conductivity, and of course we also need the melting temperature, solidus temperature, to model the contact during joining. We also need, of course, the flow curves, and you see how important it is to consider between the different phases. If you have a ferritic phase at room temperature, you might have a flow stress of, if it's pure ferrite, then it's about 205 megapascal. If you have now a martensitic material, you see it's much higher here. So this multi-phase model and this to consider the hardening during welding, it's have to be important, or is obviously important if you want to model the deformations and also the stresses correctly. To do this, we need, of course, the transformation diagrams. Next to the transformation diagrams, we also consider the transformation strains, the transformation plasticity, and the latent heat due to phase transformations. Okay. This data is already predefined, so you can take it via drag and drop, put it on the components. Here we have an additional filler material, also transforming material. We can put it on our robot. So the components are now black because we have defined everything we need. Now we have to define our mechanical boundary conditions. Maybe we have a working table, and then we can create a geometry as a mechanical boundary condition. It's extremely simple from our GUI. Maybe make it a bit nicer. Okay, so this represents our working table. Now we might have a fixing, maybe it's cylindric. Let's say here we have a fixing, and okay, maybe somewhere else we have a clamping, maybe here on the surface. Okay, these devices can be, of course, also deactivated. It's important. Maybe after 10 seconds you will release these boundary conditions. Or if you have a clamping, you might also have an initial holding force or a different stiffness and also an activation. You can choose whatever you want or what you have in real life. Now we have to define our weld path where we want to weld. For that, we should define a trajectory. We can define a few points via coordinates, and so we can also model complex structures with that. For me, to demonstrate it to you, the easiest thing is to define a node set. I take now 2 nodes along this this edge. Okay, and now I can say trajectory from node set. Okay, and I can put it via drag and drop again on my robot, and now I see I start from this point here in that direction and end here. Of course, my welding device is also an orientation. To find the orientation, I only have to, or to define the orientation, I only have to activate this checkbox, and now I can say relative to global axis or the left or right component, I want to define my axis. I can give an offset angle to it. You can also see it directly in the model. And if we want to have it on the top of the fillet, I can put on projection on surface. Next step is, of course, if I have defined the direction and orientation of my weld path, I have to define my welding parameters. As I said in the beginning, we are using mathematical descriptions to represent the heat input into our structure. The most known, or the most known model is the Goldach double ellipsoid or heat source model, and this is what I want to use now. I have only a two thin plate, so it will be a small weld pool. Okay. I also have to define my welding parameters. Maybe I have 10. I can change it here. 10 millimeters per second. Maybe I use current 70, voltage 15.7. I can say OK. If I have such, for example, a gas metal arc weld, I will have also a fillet. And for that, we also need an additional finite element mesh for the fillet. I can create one using our fillet generator. I can say, generate one, propose me some values, can have a look in the preview, and I will get such a fillet. And here I see also the expected weld pool shape. And I can say, OK. I can change, of course, the mesh quality if I want to have a finer mesh or a coarser mesh for the fillet. But here it should be OK now. Okay, now we see our Explorer tree is black, so we have nearly everything defined what we can do. But we have some additional possibilities here. If we double-click on Simufact, we can first start to say suppress mechanical solution. We only do a thermal solution. We can also activate the domain decomposition method. It's only a small model, so it should be okay. We also can model or use a mesh refinement, so the finite element mesh will be refined along the heat source area automatically during the calculation. We can also enable an unrefinement level if it cools down, and if we want to use the data again for a structural analysis, this reduces the number of elements needed. Okay, and I have said nothing about the times, but if I say nothing, the program will propose calculating end time. If I say yes, okay, save. The calculation will start. I see here if it's running a green arrow, and now I can directly go on results. And if I want to have the same view, then in my other window, I can copy the view that I see the model in exactly the same position. Here I can refresh my calculation during calculation, that I always see the latest results. And here I see the moving heat source. It's still calculating. And now it cools down. I can also have a look at the peak temperature, and also if I use the domain decomposition method on the number of domains. I didn't define this was only a vector decomposition, but for this model it's okay. Okay, so this model is the calculation is finished. If I want to compare to a cross-section of a real weld, I can also go on a welding monitor and say robot, and now I can see a cross-section, or I can activate where the cross-section is in our model, and then I can go through the cross-section if I have wrong window along this path. Okay, now I did a first thermal analysis. If I want to know more, I can, or if I want to change anything, or I want to try out or do some parameter studies, I can copy it, or I can delete the results, because if once a process is calculated, all components or all items which are be used by this process are locked. We are not allowed to change the input deck, which always already belongs to results. So I can copy it, and now I can say, please also do a mechanical analysis, use phase transformation. Maybe I will. Maybe this time I don't want to use refinement. I hope then it's faster to demonstrate live to you. And I can go on calculation again. And now it takes a bit longer because it is also do also the mechanical analysis. Okay, I can turn on my mesh, of course. Here I have my first results. Next to the temperature, we can also make, for example, if JMAT Pro I start with the temperature, the peak temperature, of course. I can make the distortion visible. The components of distortion, X, Y, Z direction. Here it's a complex situation due to the complex boundary conditions here. So it's still simple, but it would be difficult to only have a look and say the stresses and distortions has to have this distribution. We can also have a look at the effect of stresses, the stress components, the plastic history, which is deleted in the melt pool. We can also have a look, of course, on the phase fractions. If the material is molten, it's of course, if it's at high temperature, it's of course an austenitic material. This is in the fillet, there's a different material than in the base material. And during cooling, it will of course change. Depending on the cooling time, at the moment you will see nothing because it's not cooled. Or I have to refresh the results. And we get here high martensite amount in the end. It's only a small plate, and here in the beginning rapid cooling, but the rest of the weld you will get bainite. You will get more when it's cooled down completely. And if you have, for example, data of the tensile stress depending on the T8 5 times, so this is still the base material. Oh, I only calculated till 10 seconds. So I have to do it, copy it, and I have to allow it to cool it longer, because after 10 seconds it's not completely cooled down. I think the principle of the handling of Simufact welding could be shown, but I want to show you some more possibilities. We have here this Gantt diagram for only one small weld. It's unimportant, but once you have 50 or even 200 welds, then you need an overview when which weld is activated. You can also have a look inside of the components, of course. For example, if you want to see the temperature during welding, you can use this cutting tool and have a look inside from the Z direction. So this is, of course, also possible, and we have much more of these tools available here. You can insert a local system if you want to compare with measurements. Now I hope this calculation still needs to cool down. So after welding, you will get, in this case, a high amount of bainite in your weld, in the end a bit of martensite, which of course influences your distortions, which you want to investigate. Maybe it takes a bit. Okay, this was all from my side. Now we are available or free for your questions.